Have you ever stopped to wonder what makes your bank account, your online shopping cart, or even your social media feed just work? Well, the answer is this incredible 50-year-old idea that's pretty much the unsung hero of our digital world. So today, we're going to pull back the curtain on this master concept, the relational model. I mean, really think about it for a second. Every single piece of your digital life, from a friend's birthday to a flight reservation, has to be stored, found, and updated instantly and reliably. How is that even possible on a global scale? That's the huge question we're going to tackle today. Before the elegant solution we have now, the world of data was kind of a mess. Seriously, in the early days of computing, organizing information was so complex and rigid, it was like trying to build a skyscraper with Legos that you couldn't take apart once you snapped them together. So, to try and solve this, developers came up with all these different models. As you can see here, the 60s and 70s gave us these tree-like hierarchical models and these sort of web-like network models. But then in the 1980s, the relational model just completely took over. It offered a totally new level of simplicity way before these other specialized models for big data started to show up. And this is where you see the real trade-off. Those early models, they were blazing fast because all the data paths were basically hard-coded. But what if you needed to ask a new kind of question? Well, too bad. You might have to rewrite your entire application. The relational model, yeah, it was slower on the hardware of the day, but its flexibility, that was a complete game changer. And that game changer came from this brilliant IBM researcher named Edgar F. Codd. He introduced a revolutionary idea that was, at its heart, incredibly simple, but also profoundly powerful. Just organize absolutely everything into basic tables. That's it. That is the big idea. No more complex trees, no tangled networks, just simple, clean, two-dimensional tables. Honestly, the best way to think about them is as super-powered, intelligent spreadsheets that can all talk to each other. But don't let that simplicity fool you for a second. The reason this idea is so rock-solid and reliable is because it's built on a serious foundation of mathematics. This mathematical rigor is what guarantees that your data is always consistent. And here's the real breakthrough. Because of that math, you can simply declare what data you want, and the database figures out the best way to get it for you. You don't have to tell it how to do its job. So, if everything is just a table, what are these tables actually made of? Let's pop the hood and take a look at the fundamental building blocks that make this whole system tick. All right, here's a perfect, simple example. A table of employees. It looks pretty familiar, right? Just like a spreadsheet. We've got columns for ID, name, and department code, and then we have rows for each employee. We're going to use this to define our key terms. Okay, first up, the table itself, which is formally called a relation. It's basically a collection of rows. But here's the crucial part. Just like items in a mathematical set, the rows have no natural order at all. The database couldn't care less if the row for apple is stored before or after the one for lemon. Next, we have the columns, or attributes. Now, each column has a name, like name or ID, and it defines the type of data it can hold. So the ID column will only accept integers, and the name column only accepts text. This is what keeps the data so clean and predictable. And finally, we have the rows, which are formally called tuples. As you can see here, a single row represents one complete record. So going back to our employee example, that row with ID 3, name, Apple, and depart code 101, that's a complete self-contained record for that one employee. Okay, so we've got our data organized into these nice, neat tables. But how do we actually use it? How do we ask questions, find information, and maybe combine data from different tables? Well, this is where the magic of relational operations comes into play. Think of these operations as the verbs of our data language. They let us manipulate tables to get exactly the answer we need. For instance, select lets us filter for specific rows, like finding all the employees in one department. Project lets us pick which columns we want to see. And join is the real powerhouse. It's what lets us combine info from multiple tables at once, like linking an employee to their department's full name in a completely separate table. These are the fundamental actions behind pretty much every single database query. Let's see a simple one in action. Say we have this employee table with an ID, a name, and a salary. But you know what? We don't need all that information. We just want a simple list of all the employee names. To do that, we give the database a simple command in a language called SQL. We're basically telling it, select the name column from the employee table. And in the language of the relational model,
This action of picking specific columns, that's called a project operation. And boom, here's what you get back. The database returns a brand new table that contains only the column we asked for. It has projected the original table onto a smaller, more focused view. Simple, powerful, and totally predictable. Now, simplicity and flexibility are great and all, but the real superpower of the relational model is trust. It's built on this set of strict, non-negotiable rules that guarantee the integrity of the data, so you can always rely on the answers you get. And it's really important to understand that there are two types of rules here. You've got relational rules, which are universal. They're just part of the model itself, and the database enforces them. Then you have business rules, which are custom constraints that your organization defines, like, say, a maximum salary. Let's focus on those core relational rules, the absolute bedrock of data integrity. First, every single row needs a unique identifier, often called a primary key, so we can always pinpoint exactly the one we're looking for. Second, column names inside a table have to be unique to avoid any confusion. And third, you can't have two completely identical rows. That would just be redundant and ambiguous. These non-negotiable rules are what create order out of potential chaos. So, after 50 years, in a tech world where everything seems to change in a flash, why is this model still the dominant force in how we manage data? Well, it all comes down to a few core principles that are just as relevant today as they were back in 1970.
It all comes down to these pillars. Its mathematical foundation gives it unshakable reliability. Its core concept of a table is just so simple to grasp. It's flexible enough to model pretty much any kind of business problem you can throw at it. And its built-in rules guarantee data integrity. That combination right there is just incredibly hard to beat.
So why does this matter to you? Because this isn't just some abstract theory. This is the invisible engine that is literally running your life. That ATM withdrawal you just made, the flight you booked online, the item you just added to your cart, all of it is powered by the principles of the relational model.
Which leaves us with a really fascinating question to think about. The relational model provided the foundation for a half a century of digital innovation. As we generate more data than ever before in human history, what's going to be the next revolutionary idea that shapes our world for the next 50 years?